Hello, and welcome to our lecture on Kernighan and Ritchie, Chapter 5, putting some context around it. Chapter 5 is Functions and Program Structure. So, the first thing I want to call your attention to is Section 5.1. I actually think that Section 5.1 is the most poignant and beautiful section in the book. Everything you've learned up till now, everything I've talked about, size of data, etc., has led to the point where you can read 5.1 and understand every word of it. You should enjoy reading it. I think of it as like a love letter from the creators of C to future computer scientists. So 5.1 is important. We'll talk a little bit about pointer arithmetic. 5.6 we'll look at the duality between pointers and integers. Then we'll hit call by reference and call by value that are enabled in C by pointers. And then look at the biggest security hole that C has caused over the past 40 plus years, buffer overflow. Now, the chapter gets a little dense in some of the sections, and so I'll just have you skim some of those sections. This is the essential example of pointers. We have two variables, int x and y. We have a variable px, which is of type pointer. It points to an integer. That's what int star means. We store 42 in x, and we store the address of x into px using the ampersand operator. And then we use the address of x, which is in px, and then we use a lookup operator or a dereference operator, star px. It says, go to the memory location pointed to by px and load me an integer and put that into y. And so we can see when we print out x is 42 and y is 42 and px is a long hexadecimal number that is some memory location inside the actual computer. And so ampersand and asterisk and int star, the star as a sort of a modifier for a type, are the important things. One of the things that you've probably never seen in Python is the ID function. We've used functions like type and dir, and there are ways for us to inquire about variables and constants. ID is a way to ask for the ID of something. Now in CPython, and just to be clear, there are multiple versions of Python. CPython is the classic one. It's the implementation of Python that happens to be written in C. There are other implementations of Python. And so what I'm telling you with this ID function is something that will work for the moment in CPython, but not necessarily every other one. If you print it out and you say what is x and what is the ID of x, it's kind of like the address. And if you look at the documentation, it says, don't think this is the address, right? And it says the Python ID function is not intended to be dereferenceable, meaning we're not supposed to look up memory from that. The fact that it's based on the memory address is a CPython implementation detail that other Python implementations do not follow. Now, if you download the source code, kr0501.py, I actually have a completely unauthorized implementation of a lookup, a dereference. And it has to know the type of the thing that it's dereferencing, y equals deref of px, and it can then give me back that integer pointed to by the address. But this is not guaranteed to work. It's not supposed to be how it works. It just is, things have addresses, and in CPython, at least for this particular version of Python that I'm using, you can use them. Pointers gives us the ability to do call by reference. And so, if you've done Python, you see that I had a slide in an early version of my Python class that said, sorry, Python doesn't do call by reference. It only does call by value. And that means that within a function, you change the parameters and nothing happens. But some languages do have call by reference, which means the parameters that come into a function are somehow handles that allow us to actually change the values in the main programmer or where we've been calling from. So the language Pascal and C and C++, PHP, and C# have this notion, a formal notion of call by reference. And languages that don't have it are like Python and Java and JavaScript. Now there is a notion, the fact that I said this is for simple types like integers, objects are passed in, but then if you call methods in objects, you can actually change the data that the object has. But it's not like you're changing the object, you're changing the object's data. So let's take a look at a bit of code. Now the first example is actually Pascal. Now Pascal's a programming language that was written by Nicholas Wirth and in Switzerland in 1970, and it had a call by reference. And it had this notion of var, and so you're creating a function named func. It takes two parameters. One is a call by value, which is a, and another one's call by reference, which is a b. And we set a and b to two new numbers. And then in the main program, we set x equals 42 and y equals 43, and then we call the function, and you'll notice there's no extra like syntax in the function. And then we come back, and you will see that the y variable is changed and the x variable is not. And then the C version of this, we have x equals 42, y equals 43, and then when we call func, we say we're going to pass in x and then ampersand y, which is the address of y. And if you go back to the very first example in section 5.1, we're passing in a number, which we're actually passing in by value, but the value is the address. And then inside the function, we take a and then a pointer to b, pb, and we say that a is just an integer and pb is an address of an integer by adding the little asterisk there. So the address, where it's at, has been passed by value, but using that value, we can dereference it and get to the thing. So we say a equals 1, and then we say star pb equals 2. That says store 2 as an integer into the location pointed to by pb. And then when you come back, the second parameter will have been changed, y will have been changed, and x will not be changed. Now if we take a look at a few other languages, so here we have the C code again. Python, 1989, doesn't have the notion of pass by reference. And so one of the things that I think is an excellent compromise that is the case in Python is the notion of returning a tuple. Not just a single value, but a tuple return. And so that way we could, if we really wanted to get back a value, more than one value, we could return a tuple and then in the main program we assign the tuple. So if we really wanted x and y to change from inside the function, we could do so by just explicitly saying the function is going to return two values and we're going to change them both. And if we look at PHP, which is 1994, we see a very elegant, I think. Now, whenever you look at PHP, you got to realize the $sign is just part of the variable name. That's just the first character of all variables in PHP. So what we do inside a function is we say ampersand $b, which is the second parameter is b, $b, and we're expecting to change it. And you'll note that we don't change the syntax inside the function, $b equals 2, $a equals 1. The syntax doesn't change. And when we make the call, func $x, $y, we don't change that either, and yet call by reference works. So if you look at all these examples, other than the weird $sign convention, I would say that the simplest and most elegant is probably the PHP implementation, right? Because we don't have to do anything inside the function except I'm planning on changing this. Now, C#, which is much later, 2000, has this notion of ref, which is somewhat a throwback to Pascal, but also, it's the ampersand thing. And but the one thing I like about it is inside the call to func, you have to kind of agree. The calling code by saying ref x is in a sense agreeing that it is aware that x is likely to be changed by that function. And so that's call by reference. Now, we're in a C class, and so ampersand and asterisk are how we do it. So again, that's just, it's really quite straightforward inside a C code as long as you are very good at understanding what the asterisk and ampersand do in C. Another important thing that's easily understood with a very simple bit of code is pointer arithmetic. The key to pointer arithmetic is that a pointer to an integer is different than a pointer to a character. Now, both these pointers are the same size because they are an address, and addresses are all the same size. But if you add 1 to a character pointer, that actually adds 1 to the address. And if you add 1 to an integer pointer, then it adds 4. And that's because each integer takes 4 characters. And so when you're doing increments and subtracts, etc., you are when they're pointers, it increments based on the type of the thing that's pointed to. So a pointer is not just a pointer, it's a pointer to a thing with a type. And when you're incrementing and decrementing, the type that's being pointed to is more important than the fact that it's a pointer. It goes up and goes down, but it doesn't always just go up and down by 1. Pointers are not integers. So if you go back to chapter 2, there was from the book a table of the sizes of things. And so if you look in the PDP-11, integers are 16 bits. In the Honeywell 6000, they're 36 bits. In IBM 370, they're 32 bits. In Interdata 832, there's 32 bits. Now, I've added a line to this that tells the number of bits in addresses in these systems. And you can see if you compare the int numbers to the address numbers that in all the cases except the PDP-11, the integer is larger than the address, which means that there is extra space in the address, and we can almost treat addresses as unsigned integers. Now, the PDP-11 is a little weird in that 16 to 32 is a range of delivered computers over the years, and not all computers had full memory, and not all applications use the entire memory of the entire computer. So most of the time, you can conveniently put an address into an integer and then get that address back out and not have truncated that address or messed it up. So treating pointers as integers almost works, and the longer ago in history it was, the more likely it did work. Addresses are generally positive numbers that often start from 0. Sometimes heap numbers come down and sometimes stack numbers go up or whatever. But most computers did not come with a maximum memory installed, and if you're a multi-user computer, you didn't give all the system's memory to every application, and we tended to use very little memory in applications. We were very careful about it. So we just never ran into the problem of our memory addresses not fitting into integers. So in the early 70s, applications could get away with having a function that returned an address, return it as an integer, and then copy it into a pointer without conversion. And so by like the early 80s, the notion of a void pointer gave us a way to have a generic address, that is a pointer to something we don't know what type it is. Because all addresses are addresses, but what they point to is different. And so if you take a look at the alloc function, which we'll play a lot more in the next chapter, the alloc says, oh, give me 42 bytes and give it back to me as a pointer. Give me a pointer to 42 new bytes that you just allocated. So if you go in the early 70s, alloc returned an int, but then we would cast it to whatever type we wanted. So we would say alloc 42, it would give us an address, that'd be an integer, but then we'd cast it to an integer star, which is a no loss cast, and then we would store it. By the time in the 1978 CNR book, we tended to call it a char star, because the 42 is how many characters we're going to allocate. And then you would take the pointer to a character and cast it to a pointer to an integer. And so alloc of 42 would give us 14 integers, actually, I think, if I got my multiplication right. But in modern C, we have this pointer, a void pointer, which basically says, look, alloc is going to return an address, and you have to cast it to something. So alloc 42 returns a void star, which is casted to an int star, which is a lossless cast, and not something that's going to confuse the compiler, and then we store it in our int star variable. And so void, everything you'll ever touch will be using void, but I just wanted to give you a little bit of the history of it and why void's kind of not mentioned in this 1978 book. Every time in the class, I'm like, hey, it's time to learn about security, and everybody kind of groans like, oh, no. Back when I taught HTML injection and SQL injection, and cross-site scripting in all my previous classes. And here's the classic XKCD, where the mom has named their child with a bit of SQL and some single quotes and some comments, and that's all fun. It's important that we as software developers are aware of how the things that we build could be corrupted by those with evil intent, right? So it has come time to talk about that for C. Probably the single worst security hole in all of computing history, from 1950 to today, even before C was a thing, is what's called buffer overflow. And it has to do with the fact that there is no sense that a string of characters has a length. It has an allocated length, but it doesn't have a runtime length. And so when we put more data into a string than can hold the string, it just keeps on storing beyond the end of the string. It doesn't like make a little more space. And so this is from the Wikipedia page where you have an 8-character string followed by a 2-character integer or something, and we copy the string excessive, which is a 9-character, which includes 9 characters and the /0, the 0, and that completely overwrites, by just trying to write into the A string, it overwrites the B variable as well. And so that's buffer overflow. It's sort of like somehow we're going to push too much into this variable so that it extends where it's been allocated, and that never is detected, and then it keeps going on. And it means that you can do all kinds of things with buffer overflow. You can change variables, you can like turn on super user permission. Who knows? You got to look at the source code, you got to carefully construct a sort of nasty attack, but the attack vector is the fact that string arrays bounds are not checked when we're copying stuff in. And if you write bad code, or if the system writes bad code, it's just going to go wiping out memory. So it turns out that probably the worst offender of this is the getS function. And this was part of standard C for a long time. And so here what I'm doing is I'm creating a 15-character string array, character array, which is 15 elements. And I'm calling getS. And the problem with getS is like somebody's going to give us that data, and it's not us. And then I print it out. So the first thing you see is when I compile a bit of code that has getS, the compiler is upset. I have greatly simplified the errors. It comes up with 3 errors, and this is a subset of one of the errors. The compiler is telling you don't use getS. If you didn't hear what I said the first time, don't use getS. And so the compiler is not happy. But it's like, you know, people write that, so we're going to run it, okay? A.out, which starts the code, as soon as that line getS runs, the runtime of the C standard stdio.h says, before it prompts us for the data, it actually adds a print statement. It's not our print statement, it's the library saying, you really, really should not be using getS. And if you think this program is trustworthy, you're probably wrong. So I type hello world, which is 11 characters. Hello space world. Yeah, it's 11 characters. Hello world's 11 characters. I type 11 characters in. That includes the 12th character, which is the \0, and that fits into S15, a 15 element string character array in the variable S. So the program works just fine. Then I type A.out again, and it once again tells me, please don't use getS. You're going to be in so much trouble. And now I type instead a bunch of a hello and a bunch of spaces and then world, and it prints out hello, bunch of spaces and world, but it has overwritten all kinds of unknown data after the S15. So that's, you know, that's like 30 or 25 or 30 characters. And the first 15 are in S, but then the next 15 are somewhere else. And S is on the stack because it's an automatic variable in main, and it goes wiping out the rest of the stack. Now it turns out that the C runtime puts things on the stack to kind of mark or to catch this overflow. And so what happens is, as soon as that code finishes, it says abort trap 6, which is basically the C runtime saying, you know what, I'm not going to let this program proceed any further because there has been an array that got messed up. And it's not that it caught the array messing up. It didn't know how long it was. It just put characters in. But what it did is it put something after the array, and then it checked for it later, and that got wiped out. And it's like, okay, you wiped out my magic little secret, and so I'm going to not let you continue. And so we don't want you to use getS, and this is a buffer overflow. And I can give you, eventually maybe we will look at some much more complex examples of this where we try to like use something like GetS to manipulate what the program does rather than just blow the program up. But this is a very simple example of buffer overflow. So in summary, pointers are the most beautiful part of C. They're complex, but basically pointers make it so that a high-level language can function like a low-level language. If we don't have pointers, and I mean not even kind of crappy Python ones, I mean pointers that we can look up and then dereference officially and formally and not have it be a sneaky way that we're doing it, that means that you can do the things that operating systems need to do, the kinds of things that we used to write assembly language for, meaning here's a buffer of memory, we're going to copy this buffer, we're going to do another thing, and there's another buffer, and there's a linked list of all the different buffers, So understanding pointers leads you to the path of assembly language, machine language, and then ultimately hardware. So you should not rush through this material. Pointers are really, really important. Everything we're going to do from now on, pointer is I'm just going to say pointer, pointer, pointer. Just like I say object-oriented all the time, I'm going to say pointer all the time. Sections 5.7 and 5.10 through 5.12 are a little dense. So what I really want you to do is understand the stuff I just talked about and the corresponding sections. And chapter 6 will be more fun because we'll be doing much more with the pointers rather than just what is a pointer.